Welcome back. To finish off today, we're going to be talking about composite functions. Consider the following two functions, f of x equals x plus 1 and g of u equals u squared. A new function can be formed from these existing two by an operation called composition, which combines the two functions in a special way. Specifically, we set the input for g to be the function f itself. Since g simply squares any input, this results in the function x plus 1 all squared. Terminology-wise, this new function is called g composed with f, and these types of functions are called composite functions. Overall, composition is a particular way to create a new function given two existing ones. But it turns out that our main concern won't be composing functions together, but the opposite problem of identifying when a given function is already a composite function. For instance, we compose g with f above to create the function x plus 1 all squared, but if given this function to begin with, how can we tell that this was a composite function? One concrete way is to explicitly identify the component functions f and g, and show that the function can be written in the format g composed with f. This will then confirm that x plus 1 all squared was indeed a composite function. So let us set the functions f and g to be those above. Then x plus 1 all squared can be written as f of x squared, since we define f of x to be x plus 1. And this is exactly the function g, with the input set to be f of x. In other words, this is exactly the function g composed with f, and so I've demonstrated that the function x plus 1 all squared is indeed a composite function. Since the function x plus 1 is effectively nested inside of the function x plus 1 all squared, f is called the inner or inside function, while g is called the outer or outside function. When trying to decompose composite functions into these inner and outer functions, you should always attempt to identify the inner one first. In other words, what's the function that's nested within another one? Here's another example. Consider the function e to the power of 3x. Since the function 3x appears to be nested inside the exponential function, we should set our inner function f of x to be 3x, and our outer function g of u to be the exponential function e to the u. Therefore, e to the power of 3x can be written as e to the power of f of x, which in turn is just the function f thrown into the exponential function g, showing that the function e to the power of 3x is indeed a composite function. Here's one more example. Consider the function x squared minus 2, or square rooted. Since the function x squared minus 2 appears to be nested inside the square root function, we should set our inner and outer functions accordingly. Therefore, the function x squared minus 2, or square rooted, can be written as f of x square rooted, which in turn is just the function f thrown into the square root function g, showing that the function x squared minus 2, or square rooted, is indeed a composite function. So, why do we care so much about identifying when a given function is a composite function? Well, suppose you wanted to differentiate the composite function x plus 1 all squared. Expanding the right-hand side gives the following, which then allows us to differentiate using the rules we had learnt from earlier days. But what if we now increment the power of x plus 1 from 2 to something much bigger, say 7? Unlike the case when the power is 2, we would then have to spend considerably more effort expanding the right-hand side in order for us to differentiate the function. However, it turns out there's a special technique called the chain rule, which can be used to differentiate any composite function, provided we can explicitly identify its inner and outer functions. So for the function y equals x plus 1, all raised to the power of 7, we must be able to recognize that by setting the inner function u to be x plus 1, we can then write y in terms of u, namely y equals u to the power of 7. Alright, it's time to pause the module and have a go at these following practice exercises, which are designed to train your proficiency in decomposing composite functions. In particular, your goal is to identify the inner function u as a function of x, and subsequently write y as a function of u, as we had done so in the previous slide. Here are the solutions to the practice exercises.